Welcome back to The Explainer. Today, we're tackling a calculus concept that honestly gets a bad rap for being intimidating, but I promise it's actually incredibly logical once we break it down. We're focusing on the chain rule, the absolute essential method for differentiating composite functions. If you've ever found yourself totally stuck trying to find the derivative of a complex, nested equation, you're exactly where you need to be. We're going to build up your toolkit step by step so you can confidently tackle these problems. We already know the basic rules, right? We can easily find the derivative of sine of x or x cubed totally on their own. But what happens when we face a mathematical monster, like a composite function where an inner function is literally trapped inside an outer one? Take h of x equals sine of x cubed, for example. We've got our inner function, x cubed, stuck entirely inside that outer sine wave. Our standard, isolated rules just aren't enough on their own to handle this, because we're dealing with a chain reaction of changes. As x changes, x cubed changes, which in turn forces a change in the overall sine function. So, how exactly do we measure that total rate of change?
So here's our roadmap for this explainer. We'll look at the composite problem, unlock the chain rule, go through a step-by-step strategy, combine some derivative rules, and wrap up with Leibniz notation.
All right, part one, the composite problem and nested functions.
To deal with these nested functions, we use the chain rule. The official definition is that the derivative of a composite function is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Sounds like a mouthful, right? Honestly, just think of it like peeling an onion or opening Russian nesting dolls. You absolutely have to carefully work your way from the outside in. You literally can't get to the inner doll without opening the outer one first. Mathematically, if our composite function is h of x equals f of g of x, its derivative, h prime of x, is f prime of g of x multiplied by g prime of x. The absolute most crucial mantra you need to memorize here is this: derivative of the outside evaluated at the inside times the derivative of the inside. Notice how when we take the derivative of that outer function f, we leave the inner function g of x completely untouched inside the parentheses. We only differentiate g of x in that very final multiplication step. So note to self, never evaluate a derivative at a derivative. Moving on to part two, our step-by-step strategy for an actionable process. Our source lays out this fantastic, foolproof four-step strategy to keep things organized. Step one, identify your outer function f of x and your inner function g of x. Honestly, isolating the pieces really is half the battle. Step two, find the derivative of that outer function and evaluate it at the original inner function. Step three, find the derivative of the inner function completely on its own. And step four, just multiply them together. By breaking it down into these distinct, manageable parts, even the most complex functions become highly solvable puzzles. Part three, let's start combining derivative rules for some direct application. Let's look at a specific example from the text, where we need to find the derivative of 1 over the quantity 3x squared plus 1 all squared. Now, sure, we could technically use the quotient rule here, but there's a way more efficient way. We just rewrite this rational function with a negative exponent. That beautifully sets us up to use the power rule right alongside our new chain rule. Following our steps, we first rewrite the function as 3x squared plus 1 all to the power of negative 2. Now it's crystal clear. Our outer function is raising something to the negative 2 power, and our inner function is 3x squared plus 1. Applying the power rule to the outside, we bring down that negative 2, keep the inside exactly the same, and drop the exponent to negative 3. That's our outer derivative evaluated at the inner function. Next up, the derivative of the inside, which is just 6x. Finally, we multiply them together. Negative 2 times 6x gives us a numerator of negative 12x, and we just pop that over our quantity to the positive third power. A beautifully elegant result. Let's dive into another one. This time, we're combining the chain rule with trig functions, which is a super common application. We need to find the derivative of cosine of 5x squared. Step 1. Identify the pieces. The outer function is cosine, and the inner function is 5x squared. Step 2, the derivative of the outer function, cosine, is negative sine. Evaluate that at the inner function, so we write negative sine of 5x squared. Remember, do not touch that 5x squared yet. Step 3, take the derivative of the inside, which is just 10x, using the power rule. And step 4, multiply it all together. Our final result is negative 10x times the sine of 5x squared. Methodically following these steps literally prevents us from making those simple algebraic errors we all hate making. Part 4, Leibniz notation explained.
We're looking at this through a slightly different lens.
What's super interesting about this is that the two notations, prime and Leibniz, are saying the exact same thing mathematically. Prime notation is great for clearly seeing the function composition. But Gottfried Leibniz, one of the original developers of calculus, used a fraction-style notation. He defined it as dy dx equals dy du multiplied by du dx. It's incredibly powerful because it explicitly highlights how those rates of change actually link together in that chain reaction we were talking about earlier.
By letting u equal the inner function, g of x, we essentially create a bridge. The derivative du represents how the outer function changes relative to u, and du dx represents how u changes relative to x. When you multiply them, it's completely intuitive. The du terms almost appear to just cancel each other out, bridging the gap to leave you with dy dx, the total change of y with respect to x. It makes total sense why physics and engineering rely so heavily on this specific format, since it tracks the dependent and independent variables perfectly.
Finally, part 5. What's next? Tackling any composites.
To wrap up this explainer, I want to leave you with a bit of a challenge. Based on that outside-in pattern we just completely mastered, what happens if you encounter a composition of 3 nested functions? Say, k of x equals h of f of g of x. How on earth would you apply the chain reaction there? Just remember our core principle. Peel the onion one layer at a time. Take one derivative at a time and work from the outside all the way to the very inside. The pattern literally just continues. Keep that in your back pocket for the next time you face down a multi-layered calculus monster. Keep practicing those 4 steps and I'll catch you in the next explainer.